Hello, my name is Nickolay Zosimovych, and I'm professor at National Aviation University in Ukraine. The purpose of this lecture is to get going on our journey through hypersonic and high temperature gas dynamics. It starts with a little history for beginning. Okay? When and how did the first human-made object achieve hypersonic flight? And when was the first time that a human flew hypersonically? How do you think? What is so special about hypersonic flight anyway? How many questions I want to ask you from beginning, and maybe next couple too. Why is it important? And why do aerodynamicists single out hypersonics as a special flight regime, separate from the more general regime of supersonic flight? After all, both supersonic and hypersonic flight can deal with speeds above Mach 1. So what is so special about hypersonic speeds that we can prepare lecture course about this subject? These are more than just interesting questions. They are important questions that demand answer. And this lecture supplies the answer. The preliminary truths supplied here, moreover, set the stage and the tone for the rest of our discussions in this module. A study of hypersonic flow is fun. It can be technically demanding at times, as we will see, but it can also be fun. So sit back, relax, and especially enjoy this first chapter. Let it give you a smooth takeoff on our flight through the worlds of hypersonic and high temperature gas dynamics. A flight that is both intellectually and professionally rewarding. On this slide, you may see some of the recommended textbooks. And let's start with the basics history of hypersonic flight now. The day is Thursday, 24 February 1949. The pens on the automatic plotting boards on South Station are busy tracking the altitude and course of rocket, which just moments before had been launched from a site 3 miles away on the test range of the White Sands Proving Ground. The rocket is V2, one of many brought to the United States from Germany after World War II. By this time, launching V2s had become almost routine for the crews at White Sands. But on this day, neither the launcher nor the rocket is routine. Mounted on top of this V2 is a slender, needle-like rocket called the WAC Corporal, which serves as a second stage to the V2. And this state firing of the combination V2 and WAC Corporal is the first meaningful attempt to demonstrate the use of a multi-stage rocket for achieving high velocities and high altitudes, and is part of a larger program labeled Bumper by the US Army. All previous rocket launching of any importance, both in the United States and in Europe, had utilized the single-stage V2 by itself. Figure on this slide shows a photograph of the bumper rocket as it lifts off the New Mexico desert in this clear February day. The pen-plotted track the V2 to an altitude of 100 miles at velocity of 3,500 miles per hour, at which point the WAC corporal is ignited. The slender upper stage accelerates to a maximum velocity of 51 and 50 hundredths meters per hour and reaches the altitude of 244 miles, exceeding by a healthy of 130 miles previous record set by a V2 alone. After reaching this peak, the WAC corporal noses over and carries back into the atmosphere at over 5,000 miles per hour. In so doing, it becomes the first object of human origin to achieve hypersonic flight. The first time that any vehicle has flown faster than 5 times the speed of sound. Despite the pen-plotted charting its course, the WAC corporal cannot be found in the desert after the test. Indeed, the only remnants to be recovered later are a charted electrical switch and part of the tail section, and these are found more than a year later, in April 1950. The scene shifts to the former Soviet cosmodrome at Kazakhstan. The time is now 10:35 hours at Moscow time on 12 April 1961. A strange spherical object has just landed under the canopy of parachute. The surface of this capsule is charred black, and it contains 3 small viewing ports covered with heat-resistant glass. Inside this capsule is Flight Major Yuri Gagarin, who just 108 minutes earlier had been sitting on top of the rocket at the Soviet cosmodrome at Baikonur. What partially transpired during those 180 minutes is announced to the world by a broadcast from the Soviet news agency TASS at 9:59 a.m. After this announcement is made, Major Gagarin's orbital craft, called Vostok 1, is slowed at 10:25 ma by the firing of a retro rocket and enters the atmosphere at a speed more than 24 times the speed of sound. 30 minutes later, Major Yuri Gagarin becomes the first man to fly in space, to orbit the Earth and safely return. Moreover, on that day, 12 April 1961, Yuri Gagarin becomes the first human being in history to experience hypersonic flight. A photograph of the Vostok 1 capsule is shown in right parts of this slide. Later, 1961 becomes a bumper year for manned hypersonic flight. On 5 May, Alan Shepard becomes the second man in space by virtue of a suborbital flight over the Atlantic Ocean, reaching an altitude of 115.7 miles and entering the atmosphere at speed above Mach 5. Then, on 23 June US Air Force test pilot Major Robert White flies the X-15 airplane and Mach 5.3, the first X-15 flight to exceed Mach 5. In so doing, White accomplishes the first mile per second flight in an airplane, reaching a maximum velocity of 36,003 miles per hour. This record is extended by White on 9 November, flying the X-15 at March 6. The preceding events are historical firsts in the annual of hypersonic flight. They represent certain milestones and examples of the application of hypersonic aerodynamic theory and technology. The purpose of this lecture, our course here, is to present and discuss this theory and technology with the hope that the student and professional will be motivated and prepared to contribute the hypersonic milestones on the future. Let's start with hypersonic flight importance. The development of aeronautics and spaceflight from its practical beginnings with the Wright brothers' first airplane flight on 17 December 1903, and Robert Goddard's first liquid-fueled rocket launch on 16 March 1926 has been driven by one primary urge, the urge to allow us fly faster and higher. Anyone who has traced advancements in aircraft in the 20th century has seen an exponential growth in both speed and altitude, starting with the 35 meters per hour Wright flyer at sea level in 1903, progressing to 400 miles per hour fighters at 30,000 feet in World War II, transitioning to 1,200 meters per hour supersonic aircraft at 60,000 feet in the 1960s and 1970s, highlighted by experimental X-15 hypersonic airplane, which achieved Mach 7 and the altitude of 54,000 feet on 22nd August 1963, and finally capped by the Space Shuttle, the ultimate in manned airplanes, with its Mach 25 re-entry into the Earth's atmosphere from 200 miles low Earth orbit. The point here is that the extreme high-speed end of flight spectrum has been explored, penetrated, and utilized since the 1950s. Moreover, flight at this end of the spectrum is called hypersonic flight, and the aerodynamic and gas dynamic characteristics of such flight are classified under the label of hypersonic aerodynamics, one of the primary subjects of our lecture course. Hypersonic aerodynamics is different than the more conventional and experienced regime of supersonic aerodynamics. These differences will be discussed at length in Lecture 3, along with an in-depth definition of just what hypersonic aerodynamics really means. However, we can immediately see that such differences must exist by comparing the shapes of the hypersonic flights vehicles with those of more commonplace supersonic aircraft. For example, figure on this slide shows a Lockheed F-104, the first fighter aircraft designed for sustained supersonic flight at Mach 2. And this aircraft embodies principles for good supersonic aerodynamic design: a sharp, needle-like nose and slender fuselage, very thin wings and tail surfaces, 3.36% thickness to horse ratio, by the way, with very sharp leading edges. In this case, we may say that almost sharp enough to pose a hazard during ground landing, and with a low aspect ratio of 2.45 for the straight wing itself, all designed to minimize waste drag at supersonic speeds. To design a hypersonic aircraft for flight at much higher Mach number, it is tempting to utilize these same design principles, only more so. Indeed, such was the case for an early hypersonic aircraft concept conceived by Robert Garman and Hubert Drake of the NASA. Now it's a former NACA, NACA, and now it's NASA in 1953. Now modern is now this abbreviation, NASA. One of their hand drawing from an internal NACA memorandum is shown in this figure. Here we see an early concept for a hypersonic booster or orbiter combination, where each aircraft has a sharp nose, slender fuselage, and thin, low aspect ratio straight wings. The same fuselage features that is seen in the F-104, except the aircraft in this slide is designed for Mach 25. Imagine. However, in 1953, hypersonic aerodynamics was in its infancy. Contrast previous figure with another hypersonic airplane designed just 7 years later, the X-20 Dinosaur, shown in this slide. Here we see a completely different looking aircraft, one embodying new hypersonic principle that were not fully understood in early 1953. The X-20 design utilized a sharply swept delta wing with a blunt, rounded leading edge and a rather thick fuselage with a rounded rather than the sharp nose. The fuselage was placed on top of the wing so that the entire undersurface of the vehicle was flat. The X-20 was intended to be an experimental aircraft for rocket-powered flight at Mach 20. Eclipsed by the Mercury, Gemini, and Apollo manned spacecraft program, the X-20 project was cancelled in 1963 without the production of a vehicle. However, the X-20 reflected design features that were uniquely hypersonic and that were later contained in the space shuttle. Indeed, the space shuttle is shown in this slide for further comparison with the earlier concepts to previous figure. Clearly, hypersonic vehicles are different configurations from supersonic vehicles, and hence we might correctly conclude that hypersonic aerodynamics is different from supersonic aerodynamics. This difference is dramatically reinforced when we examine in this slide, which shows the Apollo space vehicle designed to return humans from the moon and to enter the Earth's atmosphere at the extreme hypersonic speed of Mach 36. Here we see a very blunt body with no wings at all. Okay? To be objective, we must realize that many considerations besides high-speed aerodynamics go into the design of the vehicles shown in this slide. However, to repeat once again, the important point here is that hypersonic vehicles are different than supersonic vehicles. And this is in part because hypersonic aerodynamics is different from supersonic aerodynamics. Be careful in this, okay? Let's go. Hypersonic flight, both manned and unmanned, has been successfully achieved. However, at the time of this our lecture, it is by no means commonplace. The era of practical hypersonic flight is still ahead of us, and it poses many exciting challenges to the aerodynamicists. Let us briefly examine some new ideas for modern hypersonic vehicles. For example, air-breathing hypersonic vehicles designed for sustained flight in the atmosphere have captured the imagination of aerospace engineers and mission planners alike. One concept is that of an aerospace plane, ideally an aircraft designed to take off horizontally from a runway and then accelerate into the orbit around the Earth. For the most part powered by an air-breathing supersonic combustion ramjet engine, sometimes they called scramjet, with most likely a rocket assist for final insertion into the orbit. It will subsequently carry out a mission in orbit or within the outer regions of the atmosphere, and then re-enter the atmosphere at Mach 25, and finally landing under power of a conventional runway. This idea was first seriously examined by the US Air Force in the early 1960s, and the combination of air breathing and rocket propulsion was intended to power the vehicle. Work on the early aerospace plane was cancelled in October 1963, mainly because of the design requirements exceeding the state of the art of the time. The idea was resurrected in the middle 1980s by both NASA and US Department of Defense, as well as by aerospace companies in England and Germany. A generic single-stage to-orbit aerospace plane is shown in this slide, representative of this second generation of aerospace plane technology. In the United States, this effort was labeled the National Aerospace Plane Program, NASP. It too was terminated in the mid-1990s, after a decade of intensive research and development. The reason was the same. The design requirements exceeded the state of the art. And this work lives on, however, in the form of more modest but focused research and technology advancements efforts. A recent success has been the X-43 Hyper-X, unmanned research vehicle shown in this slide. In November 2004, X-43 made aeronautical engineering history by achieving sustained flight at Mach 10, powered by a scramjet engine for a period of about 10 seconds. It was the first sustained atmospheric flight by a scramjet-powered vehicle. Of more importance, the flight data from the X-43 verified the predictions based on wind tunnel and computational fluid dynamic data, and proved the basic methodology used for the design of such vehicles. The door of successful, sustained hypersonic atmospheric flight has been slightly cracked open. Figure on this slide. Here the first stage is a hypersonic ramjet or scramjet powered air-bracing vehicle. And the second stage is a rocket-powered orbiter riding piggyback. Finally, Diavy mentioned the possibility of hypersonic commercial air transportation. At the time of we speaking now, there is no active program to develop even a second generation supersonic transport to replace the retired Apollo French Concorde SST. So, is a hypersonic transport only for pipe dream? How do you think? This, I think, it's not exactly. And figure on this slide shows an artist rendering circa 1985 of a futuristic hypersonic transport, sometime in the 21st century. So in this era, when we are living all together, right? Such an airplane, as shown in this figure, will be streaking through the sky, carrying passengers and cargo at Mach number of 5 and even larger. The technical, economic, and environmental challenges will be enormous. But I cannot believe it will not be happen. It is important to mention an aspect that distinguishes hypersonic atmospheric flight vehicles from conventional subsonic and supersonic airplane design philosophy. For subsonic and supersonic aircraft, the components for providing lift, namely the wings, right? Propulsion, in our case, the engines and nacelles, and volume, we mean here the fuselage, are not strongly coupled with each other. They are separate and distinct components, easily identifiable by looking at the airplane. Moreover, they can't be treated as separate aerodynamic bodies with only a moderate interaction when they are combined in the total aircraft. Modern hypersonic aerodynamics design is exactly the opposite. Figure on this slide is an example of an integrating airframe propulsion concept for a hypersonic flight, wherein the entire undersurface of the vehicle is part of the scramjet engine. Initial compression of the air takes place through the bow shock from the nose of the aircraft. Now, further compression and supersonic combustion take place inside a series of modules near the rear of the aircraft. And then expansion and the burned gases impartially released through the nozzles in the engine modules, but mainly over the bottom rear surface of the aircraft, which is sculptured to a nozzle-like shape. And hence, the propulsion mechanism is intimately integrated with the airframe. Moreover, most of the lift is produced by the high pressure behind the bow shock wave and exerted on the relatively flat undersurface of the vehicle. The use of large, distinct wings is not necessary to produce high lift. And finally, the fuel for air-breathing hypersonic airplanes, shown in this slide, is liquid hydrogen, which occupies a large volume. All of these considerations combine in a hypersonic vehicle in such a fashion that the components to generate lift, propulsion, and volume are not separate from each other. Rather, they are closely integrated in the same overall lifting shape, in direct contrast to conventional subsonic and supersonic vehicle design. And finally, return to the question asked at the beginning of this lecture. Remember, hypersonic flow, why is it important? We know a feeling for the answer. Hypersonic flow is important because of the following. And first of all, it is physically different from supersonic flight. And secondary, it is the flow that will dictate many of the new exciting vehicle designs for the 21st century. Recognizing this importance, the purpose of the present lecture and all our course is to introduce for our students to the basic fundamentals of hypersonic flow, including an emphasis on high temperature gas dynamics, which, as we will see, is an important aspect of high speed flows in general. Wherever patient, we will also discuss modern experimental and computational fluid dynamic applications in hypersonic and high temperature flow, as well as certain related aspects of hypersonic vehicle design. Such material is an integral part of modern aerodynamics. Moreover, the importance of this material will grow steadily into the 21st century, as we know yet still, as we continue to extend the boundaries of practical flight. You know, there is a conventional rule of thumb that defines hypersonic aerodynamics as those flows where the Mach number m is greater than 5. However, this is no more than just a rule of thumb. Okay? When a flow is accelerated from m equals 4.99 or even 5.01, there is no clash of thunder. And the flow does not instantly turn from green to red. Are you agree with me? Rather, hypersonic flow is best defined as that regime where certain physical flow phenomena become progressively more important as the Mach number is increased to higher values. In some cases, one or more of these phenomena might become important above Mach 3, whereas in other cases, they may not be compelling until Mach 7 or even higher. Recall from oblique shock theory, for a given flow deflection angle, the density increases across the shock wave becomes progressively larger as the Mach number is increased. Okay? At high density, the mass flow behind the shock can more easily squeeze through smaller areas. For flow over a hypersonic body, this means that the distance between the body and the shock wave can be very, very small. The flow field between the shock wave and the body is defined as the shock layer, and for hypersonic speeds, this shock layer can be quite thin. For example, consider the Mach 36 flow of a calorically perfect gas with a ratio of specific heats, gamma, equals proportional Cp over Cv equals 1.4, over a wedge of 15-degree half angle, as you can see in this slide. From standard oblique shock theory, the shock wave angle will be only 18 degrees, okay, as shown in this figure. If high temperature, chemically reacting effects are included, the shock wave angle will be even smaller. Clearly, this shock layer is thin. It is a basic characteristic of hypersonic flows that shock waves lie close to the body, and that the shock layer is thin, exactly thin, okay? In turn, these can create some physical complications, such as the merging of the shock wave itself with a thick, viscous boundary layer growing from the body surfaces, a problem that becomes important at low Reynolds numbers. However, at high Reynolds number, where the shock layer is essentially invisible, its thickness can be used to theoretical advantage, leading to a general analytical approach called thin shock layer theory. In the extreme, a thin shock layer approaches the fluid dynamic model postulated by Isaac Newton in 1687. Such Newtonian theory is simple and straightforward, and is frequently used in hypersonic aerodynamics for approximate calculations. Let's start with entropy layer. Consider the wedge shown in this left figure, except now with a blunt nose, a sketch in the right figure. At hypersonic Mach numbers, the shock layer over the blunt nose in the right figure, right, is also very thin, with a small shock detachment distance d, you may see in this diagram. In the nose region, the shock wave is highly curved. Recall that the entropy of the flow increases across a shock wave, and the stronger the shock, the larger the entropy increase. A streamline passing through the strong, nearly normal portion of the curved shock, near the center line of the flow, will experience a larger entropy increases than a neighboring streamline, which passes through a weaker portion of the shock farther away from the center line. And hence, there are strong entropy gradients generated in the nose region. This entropy layer flows downstreams and essentially wets the body for large distances from the nose, as shown in this right part, this figure. The boundary layer along the surface grows inside this entropy layer and is affected by it, because the entropy layer is also a region of strong vorticity, as related through Crocos theorem from classical compressible flow. I hope you remember this. If not, please find this in Google. And this interaction is sometimes called a vorticity interaction. The entropy layer causes analytical problems where we wish to perform a standard boundary layer calculation on the surface, because there is a question as to what the proper condition should be at the outer edge of the boundary layer. Another sub-question is a viscous interaction. Consider a boundary layer on a flat plate in a hypersonic flow as sketched in this figure. A high-velocity, hypersonic flow contains a large amount of kinetic energy. When this flow is slowed by viscous effects within the boundary layer, the lost kinetic energy is transformed, in part, into internal energy of the gas. This is called viscous dissipation. In turn, the temperature increases within the boundary layer, A typical temperature profile within the boundary layer is also sketched in this figure. The characteristics of hypersonic boundary layers are dominated by such temperature increases. For example, the viscosity coefficient increases with temperature, and this by itself will make the boundary layer thicker. In addition, because the pressure P is constant in the normal direction through a boundary layer, the increase in temperature T results in a decrease in density R through the equation of state. I hope you remember rho proportionals P over RT, where R is a specific gas constant. Okay? To pass the required mass flow through the boundary layer at reduced density, the boundary layer thickness must be larger. Okay? Both of these phenomena combine to make hypersonic boundary layer grow more rapidly than at slower speed. Indeed, the flat plate compressible laminar boundary layer thickness D grows essentially as delta proportionals m square over square root from Reynolds number. Okay? Here it's m with symbol of is free stream Mach number. A Reynolds sub x is a local Reynolds number. So clearly, because d varies at the square of m, it can become inordinately large at hypersonic speeds. And this thick boundary layer in hypersonic flow can exert a major displacement effect on the inviscid flow outside of the boundary layer, causing a given body shape to appear much thicker than it really is. Because of the extreme thickness of the boundary layer flow, the outer inviscid flow is greatly changed. The changes in the inviscid flow in turn feedback to affect the growth of the boundary layer. And this major interaction between the boundary layer and outer inviscid flow is called viscous interaction. Viscous interactions can have important effects on the surface pressure distribution, hence lift, drag, and stability on hypersonic vehicles. Moreover, skin friction and heat transfer are increased by viscous interaction. For example, figure on this slide illustrates the viscous interaction on a sharp right circular cone at 0 degree of angle of attack. And here the pressure distribution on the cone surface P is given as a function of distance from the tip. These are experimental results obtained from American researchers. If there were no viscous interaction, the inviscid surface pressure would be constant, equal to Pc, indicated by the horizontal dashes line in this figure. However, because of the viscous interaction, the pressure near the nose is considerably greater. Right? Why? The surface pressure distribution decays farther downstream, ultimately approaching the inviscid value far downstream. And this and many other aspects of viscous interaction will be discussed in our later lecture number 7. The boundary layer of a hypersonic vehicle can become so thick that it essentially merges with the shock wave, a merged shock layer. When this happens, the shock layer must be treated as fully viscous. And the conventional boundary layer analysis must be completely abandoned. Such matters will be discussed in lecture number 9. Now let's become to the next sub-question, high temperature flows. As discussed earlier, the kinetic energy of a high-speed hypersonic flow is dissipated by the influence of friction within a boundary layer. The extreme viscous dissipation that occurs within hypersonic boundary layers can create very high temperatures, high enough to excite vibrational energy internally within molecules and to cause dissipation and even ionization within the gas. If the surface of hypersonic vehicle is protected by an ablative heat shield, the products of ablation are also present in the boundary layer, giving rise to complex hydrocarbon chemical reaction. On both accounts, we see that the surface of a hypersonic vehicle can be wetted by a chemical reaction in boundary layer. The boundary layer is not the only region of high temperature flow over a hypersonic vehicle. Consider the nose region of a blunt body, as sketching in this figure, and the blow shock wave is normal, or normally normal, in the nose region, and the gas temperature behind this strong shock wave can be enormous at the hypersonic speed. For example, this figure is a plot of temperature behind a normal shock wave as a function of free stream velocity for a vehicle flying at standard altitude of 52 kilometers. Two curves are shown. First, the upper curves, which assumes a calorically perfect non-reacting gas with the ratio of specific heats gamma equals 1.4, and which gives an unrealistically high value of temperature. Look at this diagram. And second, the lava curve, right part, which assumes an equilibrium chemically reacting gas, and which is usually closer to actual situation. This figure illustrates two important points. And first, by any account, the temperature in the nose region of a hypersonic vehicle can be extremely high. For example, reaching approximately 11,000 degrees at the Mach number of 36. It's a situation where Apollo re-entry. And second, the proper inclusion of chemical reaction effect is vital to the calculation of an accurate shock layer temperature. The assumption of that gamma is constant and equal 1.4 is no longer valid. So we see that for a hypersonic flow, not only can the boundary layer be chemically reactive, but the entire shock layer can be dominated by chemically reacting flow. For a moment, let us examine the physical nature of a high temperature gas. In introductory studies of thermodynamics and compressible flow, the gas is assumed to have constant specific heat, and hence the ratio gamma proportional Cp over Cv, is also constant. This leads to some ideal results for pressure, density, temperature, and Mach number variation in a flow. However, when the gas temperature is increased to high values, the gas behaves in a non-ideal fashion, specifically as follows. And first of all, the vibrational energy of the molecules becomes excited. And this causes the specific heats Cp and Cv to become functions of a temperature. In turn, the ratio of specific heats, gamma, which is proportional Cp over Cv, also becomes a function of temperature. For air, this effect becomes important above a temperature of 800 Kelvin. And secondary, as the gas temperature is further increased, chemical reactions can occur. For an equilibrium chemically reacting gas, Cp and Cv are functions of both temperature and pressure, and hence gamma will be as function from temperature and pressure, right? For air, at 1 atmosphere pressure, oxygen dissipation, when we have oxygen in two atoms, and begins at about 2000 Kelvin. And the molecular oxygen is essentially totally dissociated at 4000 Kelvin. At this temperature, nitrogen molecule N2 dissociate into two atoms of nitrogen and begins and is essentially totally dissociated at 9000 Kelvin. Above the temperature of 9000 Kelvin, ions are formed. It means atoms of nitrogen get us excited nitrogen plus electrons. And the same with oxygen atoms decide excited oxygen plus electron. And the gas becomes a partially ionized plasma. All these phenomena are called high temperature effects. They are frequently referred to in the aerodynamic literature as real gas effect. But there are good technical reasons to discourage the use of that label, as we will see a bit later. If the vibrational excitation and chemical reactions take place, by the way, very rapidly take place in comparison to the time it takes for a fluid element to move through the flow field. And we have vibrational and chemical equilibrium flow. If the opposite is true, we have non-equilibrium flow, which is considerably more difficult to analyze. All these effects will be discussed in length in lectures through 10 to 18. High temperature chemically reactions flows can have an influence on lift, drag, and moments on a hypersonic flight. For example, such effects have been found to be important for estimating the amount of body flap deflection necessary to trim the space shuttle during high-speed re-entry. However, by far the most dominant aspect of high temperatures in hypersonic is the resultant high heat transfer rate to the surface. Aerodynamic heating dominates the design of all hypersonic machinery, whether it be a flight vehicle, a ramjet engine to power such a vehicle, or a wind tunnel to test the vehicle. This aerodynamic heating takes the form of heat transfer from the hot boundary layer to the cooler surface, called convective heating and denoted by QC is this figure. You may find QC as a downward in this arrow. Moreover, if the shock layer temperature is high enough, the thermal radiation emitted by the gas itself and can become important, giving rise to a radiative flux to the surface, called radiative heating and denoting by QR. You have the right side from QC, okay? In this figure. In the winter, when you warm yourself beside a roaring fire in the fireplace, the warmth, you feel it's not air, hot air blowing of the fireplace, but rather radiation from the hot bricks of stones of the walls of the fireplace. Imagine how warm you would feel standing next to the gas behind a strong shock wave at Mach 36, where the temperature is 11,000 Kelvin, about twice the surface temperature of the Sun. For example, for Apollo re-entry, radiative heat transfer was more than 30% of the total heating. For a space probe entering the atmosphere of Jupiter, the radioactive heating will be more than 95% of the total heating. Another consequence of high temperature flow over hypersonic vehicles is the communications blackout experienced at certain altitude and velocities during atmospheric entry, where it is impossible to transmit radio waves either or from the vehicle. This is caused by the ionization in the chemically reacting flow, producing free electrons, which absorb radio frequency radiation. Therefore, the accurate prediction of electron density within the flow field is important. Clearly, high temperature effects can be a dominant aspect of hypersonic aerodynamics. And because of this importance, Lecture 3 of this course is devoted entirely to high temperature gas dynamics. Lecture 3 is self-contained and represents a study of high temperature gas dynamics in general, a field with applications that go far beyond hypersonics, such as combustion, high-energy lasers, plasmas, and laser-matter interaction, to name just a few. Okay? And now let's start another topics of today's lecture, low density flow. Consider for a moment the air around you. It is made up of individual molecules, principally oxygen and nitrogen, which are in random motion. Imagine that you isolate one of these molecules and watch its motion. It will move a certain distance and then collide with one of its neighboring molecules, after which it will move another distance and collide again with another neighboring molecules. And it will continue this molecular colliding process infinitely. Also, the distance between collisions is different for each of the individual collisions. Over a period of time, there will be some average distance the molecule moves between successive collisions. This average distance is defined as the mean free path, denoted by L. At standard sea level conditions for air, lambda equal 2.176 times 10 in power 27 feet. A very small distance, right? And this implies that at sea level, when you wave your hand through the air, the gas itself feels like a continuum medium, a so-called continuum. Most aerodynamic problems, generally speaking, it's more than 99.9% of all applications, are properly addressed by assuming a continuous medium. Indeed, all of our preceding discussion has so far assumed that the flow is continuum. Imagine now that we are at an altitude of 342,000 feet, where the air density is much lower, and consequently the mean free path is much larger than at the sea level. Indeed, at 342,000 feet, lambda equals only 1 feet. Now, when you wave your hand through the air, you are more able to feel individual molecule impact. And the air no longer feels like a continuous substance. but rather like an open region punctured by individual, widely spaced particles of matter. Under these conditions, the aerodynamic concepts, equations, and results based on the assumption of a continuum begin to break down. When this happens, we have to approach aerodynamics from a different point of view, using concepts from kinetic theory. And this regime of aerodynamics is called low-density flow. There are certain hypersonic applications that involve low-density flow, generally involving flight at high altitude. For example, as noted in some publications, the flow in the nose region of the space shuttle cannot be properly treated by purely continuum assumptions for altitudes above 92 kilometers. This is about 3,000 feet. For any given flight vehicle, as the altitude progressively increases, and hence the density decreases, and lambda opposite increases, the assumption of a continuum flow becomes tenuous. And altitude can be reached where the conventional viscous flow, no slip conditions begin to fail. Specifically, at low densities, the flow velocity at the surface, which is normally assumed to be zero, because of friction, takes on a finite value. This is called the velocity slip condition. In analogous fashion, the gas temperature at the surface, which is normally taken as equal to the surface temperature of the material, now becomes something different. This is called the temperature slip condition. At the onset of these slip effects, the governing equations of the flow are still assumed to be the familiar continuum flow equations, except with the proper velocity and temperature slip conditions utilized as boundary conditions. However, as the altitude continues to increase, this comes a point where the continuum flow equations themselves are no longer valid, and methods from kinetic theory must be used to predict the aerodynamic behavior. And finally, the air density can become low enough that only a few molecules impact the surface per unit time. And after these molecules reflect from the surface, they do not interact with the incoming molecules. And this is the regime of free molecule flow. For the space shuttle, the free molecular regime begins about 150 kilometers. Therefore, in a simplified sense, we visualize that a hypersonic vehicle moving from a very rarefied atmosphere to a dense atmosphere will shift from the free molecule regime, where individual molecular impacts on the surface are important, to the transition regime, where slip effects are important, and then to the continuum regime. The similarity parameter that covers these different regimes is the Knudsen number. Defined as a Kn, Knudsen number, Kn proportional lambda over L. L here is a characteristic dimension of the body. The values of Knudsen is a different regime noted in this figure. And note the region where the continuum Navier-Stokes equations hold is described as Knudsen no higher than O.2. However, slip effects must be included in these equations when Knudsen even higher than O. O3. The effects of free molecular flow region around a value of Knudsen 1 and extend out of the limit of Knudsen, becoming infinite. And hence, the transitional regime is essentially contained within O.03 Knudsen and before Knudsen 1 is very small. And we have continuum flow if Knudsen is very large. We have free molecular flow and so forth. A hypersonic vehicle entering the atmosphere from the space will encounter the full range of these low density effects, down to an altitude below which the full continuum aerodynamics takes over. Because, I hope you remember, Knudsen proportions lambda over L is the governing parameter. That altitude below which we have continuum flow is greater or lesser as the characteristic length L is larger or smaller. Moreover, if we let the characteristic length be running distance supporting x from the nose or leading edge of the vehicle, then Knudsen will be lambda over x and becomes infinite when x equals 0. Look on this part of it. And hence, for any vehicles at any altitude, the flow immediately at the leading edge is governed by low density effects. For most practical applications in aerodynamics, this leading edge region is very small and is usually even ignored. However, for high altitude hypersonic vehicles, the proper treatment of the leading edge flow by low density methods can be very important. To consider low density effects as part of the definition of hypersonic aerodynamics might be stretching that definition too much. Recall that we are defining type hypersonic aerodynamics as that regime where certain physical flow phenomena become progressively more important as the Mach number is increased to high value. Low density effects are not per se might-match number effect. However, low density effects are included in our discussion because some classes of hypersonic vehicles, because of their high Mach number, will be fly at or through the outer regions of the atmosphere and hence will experience such effects to a greater or lesser extent. So let's a bit recap. To repeat, hypersonic flow is best defined as a regime where all or some of the preceding physical phenomena become important as the Mach number is increased to high value. To help reinforce this definition, figure on this slide summarizes the important physical phenomena associated with hypersonic flight. Throughout our course, fundamental aspects and practical consequences of this phenomena will be emphasized. Okay? And now let's start another topic of today's lecture. It's called Fundamental Sources of Aerodynamic Force and Aerodynamic Heating. You know, any object immersed in a flowing gas experiences a force as a result of the interaction of the body with the gas, the aerodynamic force illustrated by the vector R in this figure. The two components of R, perpendicular and parallel to the relative wind, far ahead of the body, lift and drag, respectively, as shown in this figure, right? Similarly, R can be resolved into the two components perpendicular and parallel to the core or axis of the body, the normal force N and the axial force A respectively. These forces are usually couched in terms of force coefficients. Defining the dynamic pressure Q as half rho times V squared, where rho and V are the force stream density and velocity respectively. And choosing some reference area S, we have the following by definition as lift coefficients CL proportional L over Q times S, and drag coefficients CD proportional drag over Q times S, and normal force coefficient Cn proportional normal force over Q times S, or axial force coefficient proportional Ca proportional A over Q times S, and certainly the same analogically moment coefficients proportionally more m over Q ms. In addition, consider any point of the body, and the resultant force can create a moment about this point that we decay. So here as C in our equation is a characteristic length of the body, such as the chord length as shown in previous figure. How does nature exert an aerodynamic force on the body? To help answer this question, pick up this book and hold it stationary in the palm of your hand. You are exerting a force on the book equal to its weight, right? This force is communicated to the book by the skin of your hand being in contact with the bottom cover of the book. This is the only way that the book knows that you are exerting a force on it, by contact of the book surface with your hand, right? Similarly, the surface of the body in figure A in left side is in contact with the air, the molecular layer of an air immediately adjacent to the body surface. The only way that the body feels the presence of the air is through the pressure distribution and shear stress distribution exerted on the body surface, that is in contact with the air, right? As illustrated on the figure B on the right side, the pressure acts locally normal to the body surface, and shear stress, which is caused by friction between the body and the molecular layer of air just adjacent to the body surface, and acts locally tangential to the surface. Let's be the distance along the body surface measured from the leading edge or nose of the body as shown in figure B. The variation of pressure with distance along the surface denoted by P from S, yes, P from S, is the pressure distribution. And the variation of shear stress with distance along the surface denoted as a tau, tau from S, the shear stress distribution. Clearly, pressure and shear stress are distributed loads acting on the body, and when integrated over the complete surface area of the body, give rise to the resultant aerodynamic force vector R, right, as shown in this figure A. The two hands of nature that reach out and grab hold of the body, exerting a force on the body, and the pressure distribution and even shear stress distribution exerting on the body surface. These are the two fundamental sources of aerodynamic force, and that is all there is. Except in case where viscous interaction is dominant and or flow separation take place, the surface pressure distribution is essentially by nature an inviscid flow phenomenon. Part 1, in lectures from 2 to 5 of our course, deals with hypersonic inviscid flow. Much of the material in Part 1 is focused on the calculation of pressure distributions over the surface of hypersonic aerodynamic shapes, and thus leading to the prediction of lift and wave drag, a pressure effect. Okay? Shear stress is a viscous flow phenomenon. Part 2, lectures from 6 to 8 of our course, deals with viscous flow. Some of the material in Part 2 is focused on the calculation of shear stress distribution over the surface of hypersonic aerodynamic shapes, and thus leading to the prediction of skin friction drag. The surface shear stress is dictated by the velocity gradient at the surface. You see this expression on the middle of the slide, where du over dy W is the velocity of gradient of the wall, and mu sub W is the viscosity coefficient of the wall. Any object immersed in flowing gas also experiences heat transfer at the body surface. For most practical cases in high-speed aerodynamics, heat is transferred from the gas into the body, aerodynamic heating. Okay? For low-speed subsonic flows, aerodynamic heating through present is small and not generally a player. For supersonic flows, however, aerodynamic heating becomes a consideration. For hypersonic flows, aerodynamic heating is a major player, so much so that it dictates the configuration design of most hypersonic vehicles. The sources of aerodynamic heating to a body are related to the hot gas in the flow field around the body. The boundary layer adjacent to the body surface is hot because the high kinetic energy hypersonic flow entering the boundary layer and is slowed by viscous effects within the boundary layer, dissipating the kinetic energy and transforming it in part into the internal energy of the gas. The gas in the inviscid portion of the shock layer between the shock wave and the body is hot because it has come through a strong shock wave. Shock wave heating and intense viscous dissipation are the causes of the hypersonic flow over a body being hot. Nature, in turn, pumps some of this heat energy into the body in the form of aerodynamic heating. There are two physical sources of mechanisms that nature uses to transfer the heat into the body: thermal conduction and radiation. Let us examine each one of these mechanisms in turn. Thermal conduction takes place when a temperature gradient exists in the gas, and from Fourier laws of heat conduction, the heat transfer of the surface Q sub W is given by this expression: minus K sub W times dt over dy. K sub W is the thermal conductivity of the gas at the wall, and this expression dt over dy is the temperature gradient in the gas at the wall. The minus given this sign denotes that the heat is conducted in the opposite direction of a temperature gradient. For example, reflect again on the boundary layer temperature profile sketching on this slide. The temperature gradient at the wall is clearly seen, At the wall, the gas temperature increases with distance above the wall, and hence the gradient dt over dy is a positive quantity. Consequently, Q W flows into the wall in the negative direction. Yes? And thermal conduction is one of the nature's ways to transfer heat to the surface of a body. The hand of nature that does this is not the temperature of the gas at the wall, but rather the temperature gradient in the gas at the wall. And part 2 of our course deals in part with the calculation of temperature gradients at the wall, and hence the conductivity heat transfer at the surface. Thermal radiation is the other hand that nature uses to heat a body or cool a body. If the temperature of the flow field around a body is hot enough, significant thermal radiation from the gas to the body takes place. How hot is hot enough? For air, if the shock layer temperature is about 10,000 Kelvin or higher, radiative heat transfer from the hot shock layer to the cooler body becomes a player in the overall heating of the body. Examples are space vehicles entering the Earth's atmosphere at superorbital velocity, such as a polar lunar return capsule, where the shock layer temperature reaches as high as 11,000 Kelvin. And almost 30% of the total heat transfer to the Apollo during atmospheric entry was caused by namely radiative heating. For the Galileo probe entering the Jovian atmosphere at 15 kilometers per second, where the shock layer temperature exceeds 15,000 Kelvin, more than 95% of the total heat transfer was radiative heating. Radiative heating will be treated in lecture 18. We should note that the solid surface of the body radiates energy away from the surface. This is a form of cooling of the surface, radiative cooling. Solid bodies emit radiation primarily in the infrared part of the spectrum. Imagine when you stand in front of a fireplace or comfortably sitting on a cold winter day and enjoy the heat from the fire. Most of the heat you are feeling is coming from infrared radiation emitted from the hot bricks or stone of the walls of the fireplace. Moreover, the radiative energy emitted from the surface of a solid body is a function of the surface temperature, following the T in power 4 variation of a black body. Surface radiation, therefore, can be used effectively as part or all of the thermal protection mechanism for hypersonic flight. In summary, the two sources of aerodynamic heating are the temperature gradient is the gas at the body surface, adding heat to the body by means of thermal conduction, and the hot temperature that exists globally through the shock layer, adding heat to the body by means of thermal radiation from each hot fluid element in the flow field. And frequently, the former mode of heating is called convective heating. Also, thermal conduction at the surface is the hand that nature uses to transfer the energy to the surface. The latter mode of heating is simply called radiative heating. Now let's start another topic today's lecture called hypersonic flight path from velocity altitude map. Also, this is a course on hypersonic and high temperature gas dynamics. And we must keep in mind that the frequent application of this material is to design an understanding of hypersonic flight vehicles. In turn, it is helpful to have some knowledge of flight paths of these vehicles through the atmosphere and the parameters that govern such flight paths. This is the purpose of the present section. We will examine the flight paths of lifting and non-lifting hypersonic vehicles during atmospheric entry from space. Consider a vehicle flying at a velocity v. A flight path inclined at the angle u below the local horizontal and shown in this figure. The forces acting on the vehicle lift, perpendicular to the body, and drag, and certainly weight, W here. The thrust is assumed to be zero, and hence we are considering a hypersonic glide vehicle. Summing forces along the perpendicular to the curvilinear flight path, we obtain the following equations of motion from Newton's second law. Along the flight path, we got that expression, W times sine theta minus drag equals m times dv over dt, acceleration, right? And perpendicular to the flight path, L minus W times cosine theta equals minus m times v squared over r. In this equation, r is the local radius of the curvature of the flight path. For most entry conditions, theta is small, and hence we assume as sine theta approximately equal 0 and cosine theta is approximately equal 1. For this case, our first equation becomes, noting that mass, this is V over W over G, and we get the expression minus drag proportions W over G times dV over dt, or acceleration. And next equation, L minus W proportions minus W over G times V squared over R. The drag can be expressed in terms of the drag coefficient CD, as d equal half of the rho v squared s times cd, okay? And where rho is the free stream density, and s here is the reference area. Hence, we can become next equation, as you may see here, minus 1 over 2 rho v squared s times cd proportions w over g times dv over dt. Rearrange these equations, we obtain next one, minus 1 over g times dv over dt. In the right side, we get w over cd times s, is opposite minus 1s, and times rho v squared part. In these equations, v over cds is defined as a ballistic parameter. It clearly influences the flight path of the entry vehicle via the solution of previous equation. For a purely ballistic re-entry, we mean no lift. So WCD times S is the only parameter governing the flight path for a given entry angle. Returning to our previous equation and expressing the lift in terms of the lift coefficient, CL as the L proportions 1 over 2 rho v squared SLC minus SLC, we obtain this equation, as you may see for us. 1 over 2 rho v squared SL S times CL minus W equals minus VW over G times V squared R. V over CL, you remember, is the lift parameter, It is clearly influences the flight path of the lifting entry via the solution. So that in using both two equations, we may illustrate importance of W, CL, and CD, these two ballistic parameters. And that was determining the flight path through the atmosphere of a vehicle returning from space. Such flight paths are frequently plotted on a graph of attitude versus velocity, a velocity-attitude map. An example of which is shown in this slide. Here two classes of flight paths are shown. First of one is the lifting entry covered mainly by V over over CLS. And second ballistic parameters govern mainly W over CD times S. The vehicle enters the atmosphere at either satellite velocity, such as from orbit, okay, or at escape velocity, such as a return from a lunar mission. As it flies deeper into the atmosphere, it slows as a result of aerodynamic drag, right? Giving rise to flight paths shown in this figure. But you should note that vehicles with larger values of W over CLS and W over CD times S penetrate deeper into the atmosphere before slowing. The lifting entry curve initiated by escaping velocity is equal near the 100 pounds per square feet pertains approximately to the polar entry capsule. Velocity attitude maps are convenient diagrams to illustrate various atmospheric it's better say aerothermodynamic regimes of supersonic flight. And they will be used as such in some of our subsequent discussion. So let's give some summary. The major purposes of this lecture have been motivation and orientation. Motivation as to the importance, interest, and challenge associated with hypersonic aerodynamics, and orientation as to what hypersonic entails. For the remainder of this course, our purpose is to present and discuss the important fundamental aspects of hypersonic and high-temperature gas dynamics, and to highlight various practical applications as appropriate. Towards this end, our course organized into the three major parts, as diagrammed in this slide. And these three parts are as follows. Part 1, inviscid flow. Here the purely fluid dynamic effect of large Mach number is emphasized, without the added complications of viscous and high temperature effects. In these parts, we examined what happens when freeze-free Mach number becomes large and how this influences aerodynamic theory at high Mach number. Here we calculate pressure distribution on surfaces and obtain the aerodynamic lift and wave drag on hypersonic bodies. Part 2, viscous flow. Here the combined effect of high Mach number and finite Reynolds number will be examined. The purely fluid dynamic effect of hypersonic flow with friction and thermal conduction will be presented. Again, high temperature effect will not be included. Here we calculate the shear stress on the surface and the resulting skin friction drag on the hypersonic bodies. In addition, we calculate the temperature gradient in the gas at a surface and the resulting aerodynamic heating to hypersonic bodies because of the thermal conducting. You remember, convective aerodynamic heating. And part 3, high temperature flow. Here the important aspects of high temperature gas dynamics will be presented. Emphasis will be placed on the development of basic physical chemistry principles and how they affect both inviscid and viscous flow. High temperature flows wind application in many fields in addition to hypersonic aerodynamics, such as combustion processes, explosions, plasmas, high energy lasers, etc. Therefore, part 3 will be a self-contained presentation of high-temperature gas dynamics in general, along with pertinent applications to hypersonic flow. Here we also calculate the radiative heating of a hypersonic body caused by intense radiation from very high temperature shock layers. And figure on this slide is a block diagram showing each one of the 3 parts just discussed, along with the major items to be discussed under each part. In essence, this diagram is a roadmap for our excursions on hypersonic and high temperature gas dynamics. So, this diagram is important, and we will refer to B in often to see where we are, where we have been, and where we are going in our presentation. So I hope you enjoyed this lecture. Next lecture, we will be studying inviscid hypersonic flow. And in this moment, I hope it's more than enough for first time. And I'm looking forward to seeing you next time to continue study our favorite course. Bye.